In this video, I'm going to introduce you the field induction. Field induction. So Faraday mentioned is an electric field is induced. Is induced in any region of space in which a magnetic field is changing with time. When you have a changing magnetic field, electric field is induced. So here, Maxwell is the one who put all these ideas together, and he counterpart to this, saying that a magnetic field, now it's a magnetic field, right, is induced, we know that too, in any region of space, the space and time, in which an electric field is changing with time. So this is the Maxwell's equation, very, very famous one. Let me just write out the Maxwell's equation. You don't need to know, of course, but here Maxwell's actually put these two together and he made into an equation. Delta E equals rho over epsilon naught. This one shows that if you have a monopole, so one charge, this one you have a charge, then it generates electric field everywhere in space. And then this one shows that there's no magnetic monopole. You don't magnetic poles always comes in dipoles. And then you have electric field generated when you have a change in time with magnetic field, and also magnetic field is generating in space, everywhere in space, when you have current and change in electric field with time. So that's what it means here. What this one is saying is that there is the, if you have a stationary electrons, right? Remember, stationary charge produce electric field. Electric. Not the, no magnetic field. When Q is at rest. Only when Q is moving, then it generates both the changing. If it's moving, then you want to have an electric field and also magnetic field, right? So that's what it means by changing moving electron. Mu naught J is the one that's moving current, all that kind of stuff. No magnetic field, and then moving charge. Moving charge means both electric field and magnetic field. All right, and then you have a changing magnetic field induces electric field. Changing electric field induces magnetic field. So this is called field induction. So let's see. Mm, we have a, let's say I have a, it's better to use electron, but for convention, I'm just going to use a plus Q, right? It is typically the electron that's making the motion, but just use the plus Q. Let me see here, plus Q. So let's see, if plus Q is moving upward, then it generates electric field. And electric field is generated, right? And this electric field is going to move later on. This is going to go, it's going to move. It takes a signal will be propagating everywhere in space, but it has a propagation speed. So it moves. And then later on, this charge Q is going to move farther. So it's going to go upward, upward, more up, right? Maybe it goes down, down. This signal will be propagating. Maybe it goes down, 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 down. So this is how, so everywhere, it takes time for signal to propagate, but it propagates like this, and it fills up the space. So you see, this is the electric field that's generated as the oscillation of electric charge, right? This is the electric field. And electric field oscillates as plus Q oscillates. So when you have an electric charge that's moving up and down, that's also generating the up and down electricity everywhere in space. So it's just going to go out like this, up and down, up and down. But we also know when you have a change in electric field, right, that also induces magnetic field. And this change in electric field induces magnetic field that's perpendicular to the electric field. So as the electric field is being generated and it's changing up and down, there's going to be a magnetic field. It's being generated something like this. So when you have this much, when you have this much, this much, it's going to be moving. Eventually it goes here. If it's here, eventually it goes here, and it just goes everywhere. It propagates. And then goes this way, that way, this way, propagates. So you see the magnetic field, as the electric field is induced, magnetic field, oscillating magnetic field with the same frequency is also induced magnetic field. So also magnetic field oscillates as plus Q oscillates. So oscillation of electric charge produces oscillation of electric field and oscillation of a magnetic field, and this is called wave. It's called electromagnetic wave. What is this electromagnetic wave? And then I said that this electric field and moving electric field and magnetic field, it propagates, right? Propagates on this throughout the space. They propagate. What is the speed of this propagation? Which is speed of light. C equals 3 times 10 to the 8 meter per second squared in a vacuum. So what is that? Electromagnetic wave is the light. So let me see. I can just have a metal. So if I just have a charge that's moving up and down, 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 then I generates the induced electric field, magnetic field, induced electric field, magnetic field, and propagate as light. So this is the punchline of the course, the whole semester. Field induction. Electromagnetic induction is a two-way street. Faraday said that an electric field is induced by any region of a space in which a magnetic field is changing with time. Then Maxwell's counterpart saying that a magnetic field is induced in any region of a space in which an electric field is changing with time. So when you have a changing, if you have an up and down, a charge that's moving up and down, it generates electric field, changing electric field, and this changing magnetic fields are both induced and travel throughout the space as electric magnetic waves known as the light, speed of a light. Okay, so this is the end of the video, and I'll see you.